Let's talk about light, electromagnetic waves, and vision. One of the big questions that happened over a long time is light really a wave or a particle? Now, we've been talking about it as a wave, but there's been controversy between what light really is. A guy named Huygens thought light was basically a wave. And Huygens and the people that followed him would keep coming up with different demonstrations and examples where light behaves like a wave. It goes around things like water waves would. Newton, on the other hand, said light was a particle, that it was a discrete thing that traveled from one place to the other. And the people that followed him would again come up with examples of where light behaved like a particle. Well, this argument went on for a few hundred years until Einstein came along and settled the argument. He said light was both a wave and a particle, and he called it a photon. And basically, what a photon is a wave packet that in certain situations will behave like a wave, in other situations will behave like a particle. And we call that the dual nature of light, that it can behave as both a wave and a particle depending on the situation you put it in. So if you set up an instrument or a lab or a demonstration where you need light to behave like a wave, light behaves like a wave. If you set up a demonstration or lab or whatever, and you need light to behave like a particle, it behaves like a particle. It's very convenient that way. So that's the dual nature of light, that light can be both a particle and a wave, and we call that fundamental quantity of light a photon. Now let's take a look at light a little bit further. And anytime I talk about light, I mean anything in electromagnetic spectrum. We normally lump all that stuff in with just light, but any of the electromagnetic spectrum like radio waves, microwaves, infrared, ultraviolet, X-rays, gamma rays, any of those, we kind of combine that and we just call those light of different versions. Visible light just happens to be the part of that spectrum that our eyes can detect. And all these electromagnetic waves are transverse waves. And they don't need a medium to travel through. Electromagnetic waves of any type can travel through space. That's how we get the light and heat and energy from the sun. And so they don't need a particular material to travel through. And so they all have the same speed. Radio waves through X-rays and gamma rays and light and infrared and microwaves, they all have the same speed because they're essentially the same type of wave. We're just seeing it in different frequencies and wavelengths. Now, how do we come up with the speed of light? The speed of light's very, very fast. You're not going to really time that with a stopwatch. The first two instances of people that tried to find the speed of light that I know about, one of them was Galileo. And what he did was he climbed to the top of a hill with their version of a flashlight. It was a lantern that had a shutter on it that he can open up and send out a beam of light. And he sent one of his students over to another hill with a lantern. And Galileo would open his lantern, send out a beam of light. The student, when he saw the beam of light, would open up his lantern, send a beam of light back to Galileo, and he would time it with his pulse. And so he would get a time and a distance so he can figure out a velocity. And to check his math, he sent his student out to a hill that's further away. They repeated the experiment and got essentially the same time. And Galileo thought that was weird because since he sent him to a hill that was further off, it should have taken longer for that light to get there and come back. And Galileo said that doesn't make sense. And so either light is instantly everywhere in the universe as soon as it comes into being, or my experiment's simply not good enough to determine the speed of light. And he finally decided it's probably his experiment. What he was really doing is simply gauging their reaction time. And so that threw everything off, and he kind of gave up doing that. And a guy named Romier, he wasn't actually looking for the speed of light, and he almost figured it out. He was looking at one of Jupiter's moons, particularly Io. And he would set up this table and this model where he could exactly predict when Io was going to go behind Jupiter and when it was going to become visible on the other side. And at certain times of the year, his chart was very accurate. Then at other parts of the year, when the Earth was essentially on the other side of the sun, his data was off by several minutes. And what he did was he took what he knew as the diameter of the Earth's orbit and divided by the time that was off, and he got a value. It wasn't the speed of light, but it gave us a place to look. In physics, if we know kind of where the answer is, how big it is, we're actually pretty good at figuring out what the answer is. So he gave us a starting point for what the speed of light is around. And then a guy named Albert Michelson. Now, Albert Michelson was the first American to win any Nobel Prize at all. And he happened to win it in physics for this experiment. And what he did was he set up an 8-sided mirror that looks sort of like a traffic light or a traffic stop sign. And each side had a mirror on it. And he set that on top of a turntable. And he set up a beam of light that would hit one side of that mirror, bounce off, hit a mirror that he placed quite a distance away. That light would bounce back, hit the other side of that 8-sided mirror, and then reflect into his eye so he could see it. Now, so he knew a distance out to that mirror and back. The way he got the time was he spun the mirror. He would only be able to see that pulse of light if the turntable turned exactly 1/8 of a turn. If it turned less than that, the beam of light would shoot up and you wouldn't see it. If you turned more than that, the beam of light would shoot off and you wouldn't see it, only when it turned exactly 1/8 of a turn. And so he could determine the speed of his turntable and figure out how long it took to turn exactly 1/8 of a turn, and that was his time. So now he had a distance and a time. He divided and got the speed of light, which is 3 times 10 to the 8th meters per second. So 300 million meters every second. To give you an idea, it takes light from the sun to the earth to go from the sun to the earth in about 8 minutes. So light's incredibly fast, but it's still not as fast as we think it is considering the size of the universe. So how does light interact with other stuff? Well, it does it in 3 different ways. It can be transparent, translucent, or opaque. Transparent means light passes through and doesn't get distorted. So an example is your regular windows of your car or your house. They let you see out. You can see clearly. You can tell exactly a person that's outside or a car or whatever. You can tell exactly what things is. You can see clearly through it. Translucent, light does pass through, but it gets distorted. And some examples are that I have here: stained glass or textured windows, like you would have maybe on a shower or something, where or a church window, where you can see light coming through, and you may even be able to tell that that's a tree or that's a person, but not enough detail to tell who that person is. Opaque simply means light can't pass through. So it's like a solid wall or a table or something. Light simply does not pass through. Now, different parts of the electromagnetic spectrum are these things to different materials. For example, glass is transparent to visible light, but to ultraviolet, it's opaque. So you can sit inside your car with the windows up and get really hot on a summer's day, but not actually get a tan. You may turn red because you're hot, but you won't tan up. One example of this is what my uncles, when they were in high school, decided to skip school and go driving around. And this was in the 1960s. And they didn't have air conditioning in the car, so they had the windows rolled down. The older brother was driving with his left arm hanging out the window. The younger brother was just sitting there in the passenger seat with his right arm hanging out the window, and they drove around, cruised around town all day long, and then they came back home. As soon as they did, my grandmother knew that they weren't in school because the older brother, since he had his left arm out the window, his left arm was sunburned, but the rest of him was still as pale as normal. The younger brother, his right arm was sunburned, the rest of him was pale as normal. And she decided that they couldn't get those particular sunburns sitting in the classroom, so she knew they skipped class. But like your bones are opaque to x-rays, while your flesh is more transparent to translucent for x-rays. And so depending on the material and the energy, the electromagnetic wave you're hitting it with, each thing can have a, whether it's transparent, translucent, or opaque to that material. It just depends on which one it is. Now here's an example of the electromagnetic and visible light spectrum. So electromagnetic spectrum, I always start off over on the left with radio waves and go across to the right, ending in gamma rays. So we got radio waves, microwaves, infrared, visible light, which is all the colors of the rainbow, ultraviolet, X-rays, and gamma rays. So that visible light is all the colors of the rainbow, that Roy G. Biv that we memorize. Actually, Newton came up with that Roy G. Biv. He actually added indigo in there because he was very superstitious for a physicist. And without indigo, we just have 6 colors, and he thought 7 was a lucky number, so he threw indigo in there just to get 7. But the unique thing is green is the color that's most sensitive to our eyes. And we'll get into vision a little bit later. So let's talk about color. Well, if we mix all the colors of the rainbow together, we get what we call white light. So Newton took a prism, took a beam of white light through that prism and created the rainbow. He also reversed that. He took that rainbow and put a second prism there to gather that light and recombined them and got visible light back again. So he proved that you can separate light into the different wavelengths, and then you can recombine them to get white light back again. And so for us, we like to break things into 3 primary colors of light. This is different than the primary colors you learned in art class. In art class, you learned the primary colors was red, blue, and green. That's subtracting colors. Like for paints, if white light hits blue paint, that blue paint will absorb all the other colors except for blue, and blue gets reflected back off. Red paint will absorb all the colors except for red and reflect red back, and that's why we see it as red. What we're talking about here is actual light, not paints, not pigments. And so if you mix those 3 different colors of light, red, blue, and green, you get all the other colors. And so for example, if you mix red light plus blue light plus green light, we should get white light back. But what if we just mix red and blue light? We should get magenta. Red and green, we should get yellow. Blue and green, we get a color known as cyan. But we can get all the colors that we see just by mixing those 3 colors in different amounts. We can get every color that a person can see. Now, how does our vision work? Well, first, light comes through the cornea, through our pupil. Our pupil gets bigger and smaller to control the amount of light that comes into our eyes so we don't burn out our back of our retina. Then the lens helps focus that light onto the back of your retina. And your retina is made up of 2 different types of cells, rods and cones. Rods are your black and white vision. Rods work in low light situations where you don't have enough light to actually activate the cones to detect color very well. And so under low light situations, you can't tell color very well. You might be able to see fairly well, but you can't tell the color of objects. You may not be able to tell the difference between a red and a blue object because we don't get enough of that light into our eye. When there is enough of that light, your cones kind of kick in, and your cones give you your color vision. And we have three different types of cones: red, blue, and green. Now, on the old cathode ray tube TVs, the CRTs, the big glass things that I had when I was a kid, when you turned them off, a lot of times the picture like shrunk down to the middle, and you saw a red dot, a blue dot, and a green dot, where that TV, RGB, red, green, blue, would just use those same colors, just use red, blue, and green, and it would mix those colors to give you the picture on the screen, just like your retina takes in those three different colors in different combinations, different amounts, to give you your vision that you see. If you happen to have a deficiency in one of those types of cones, either red, blue, or green, you're considered colorblind or a color deficiency now. Now that doesn't mean if you're red colorblind that if anybody's wearing red, they're invisible to you. That doesn't happen that way. It's just that color will look something different. It may look brown instead of red. And so you'll still see that object, but it won't look the same color as what anybody else would see. All right, going to the Doppler effect. We all know what the Doppler effect is. If you've ever been near the road and a car passed you, you hear this sound as it goes by. So as it's coming towards you, it sounds a higher frequency. Then as soon as it passes you, the sound drops to a lower frequency. Now, if you're in that vehicle and there's no apparent motion between you and the car, I mean, you're sitting inside the vehicle, you hear the same sound all the time. But outside the vehicle, as it's coming towards you, the sound will sound a higher frequency. And as soon as it passes you, it'll drop to a lower frequency. Light does the same thing. And any of the electromagnetic waves did the same thing. As the two objects get close together, they're moving towards each other, light will get what we call blue shifted. The frequency will be higher. And so higher frequency means more towards the blue. If it's moving away from you, that's what we call red shifted. It gets stretched out. So we get a longer wavelength, lower frequency. It gets what we call red shifted. And we can use that to actually detect how fast that object is either moving towards us or away from us. That's how radar guns work for the police. They send out a specific signal, it bounces off your vehicle, and if you're moving towards the officer, that wave gets kind of scrunched up, so it comes back at higher frequency, shorter wavelength. They can tell by the difference how fast your car is moving. Same thing if it's moving away from you, except now the wave will get stretched out and be a lower frequency, longer wavelength. And again, when it gets back to the officer, they can tell, or the computer chip inside the radar gun can tell how fast you're moving by the difference in the apparent frequency. Now, we talked about the wave equation before. This is the wave equation for electromagnetic waves, where c is the speed of light. C is at 3 times 10 to the 8th. And we're just going to talk about the concept and the relationship between these things right now. That little upside down y is the Greek letter lambda. It stands for wavelength, and f stands for frequency. So the speed of light is pretty much a constant, 3 times 10 to the 8th meters per second. So the higher the frequency, the shorter the wavelength. As one goes up, the other one must come down. And so if we look at our electromagnetic visible light spectrum, radio waves will have the lowest frequency and the longest wavelength, while gamma rays has the highest frequency but shortest wavelength. Now, visible light fits in there between infrared and ultraviolet. Infra is a prefix that means below or beneath. So infrared literally means beneath red. Ultraviolet, ultra is a prefix that means above or beyond. So ultraviolet means beyond violet. And so that was one of the first ones that we detected outside of visible light. And they were named by their position. So red will have a longer wavelength, lower frequency than orange. Violet will have a higher frequency, shorter wavelength than blue. And so on my diagram there, as you move towards the right, we go higher frequency, shorter wavelength. As you move towards the left, you get a lower frequency, longer wavelength. So microwaves have a lower frequency, longer wavelength than the color yellow. Blue will have a lower frequency, longer wavelength than X-rays. As you move towards the left, you get a lower frequency, longer wavelength. As you move to the right, you get a higher frequency, shorter wavelength. Now, when Einstein coined this term a photon, there was another guy called Max Planck that wanted to figure out the relationship between these frequencies and how much energy that those waves have. He came up with this equation. Energy equals a constant that he figured out times the frequency. And as we go through the same way, anything towards the left will have a lower frequency, and since that's a lower frequency, they'll also have a lower energy. Anything towards the right, higher frequency, higher energy. So radio waves have a low frequency, long wavelength, and low energy. Gamma rays have a high frequency, high energy, short wavelength. And one way that you can remember this is with the story I'm getting ready to tell you. Let's say that your favorite basketball team gets a brand new basketball player. 7'4", red-headed kid. After you got redhead, usually you don't bother learning their name, they're just red. Okay, so 7'4" red happens to be dating a cheerleader. 5'2" violet. And so red, very tall, violet, really short. Let's say they go walking to class hand in hand, so they're walking at the same speed. Red's taking these big, long steps, so long wavelength. Doesn't have to take very many of them to get any place because he's got really long legs. While Violet's walking with him, since she's shorter, she's got shorter legs, so she's gonna have to take a bunch of steps to keep up with Red. So a bunch of steps means high frequency. Her legs are shorter, so her stride is shorter, so shorter wavelength. Again, Red, long steps, long wavelength, low frequency. Violet, a bunch of steps, so high frequency, short wavelength. And I've learned this, that sometimes really tall people can also be lazy. So Red has less energy than Violet, which is the cheater that's always bouncy and peppy and stuff like that. If you remember that example, then you remember, if you look at the visible light spectrum, Roy G. Biv, that orange is going to have a lower frequency, lower energy, longer wavelength than green does, because it's closer to red. Anything closer to violet will have a higher frequency, higher energy, shorter wavelength. Just keep that in mind. All right, thank you.